Okay. So thank you for introduction. And today is the second and last lecture on my part. And yesterday I introduced the basic analysis of Brasov equation, what is the stationary state and what is, how we can judge the stability of the stationary state. And before going to the, so I promised I will talk the physics today. And before going to the details of the physics, I a little bit continue the stability part, so with giving a simple example. So I listed B5 stability. The continuous part. So let us consider the simple model of the Hamiltonian mean field model. So it is the interaction function is minus cosine q. So minus means the attractive force. And then it gives a Hamiltonian depending on F and Q and P and T. So it is P squared over 2 minus potential function. Okay, and then we consider the very simple Maxwell distribution, especially homogeneous Maxwell distribution. So stationary state, our stationary state is, so here's a normalization factor to get the integral over dq dp is 1, so not necessary part, not important part. And then we introduce the temperature T. But don't confuse this T as we are considering the canonical state or not. Because normally temperature T implies that the system is contacting with the heat bath with temperature T. But now this T is just a parameter to make a family of stationary state. So this does not mean the heat bath. So in other words, we always consider the microcanonical state. And then the so-called spectrum function, which is I introduced yesterday, is big lambda for Fourier model N. And for this HMF model, we get P for N equal plus minus 1, and then only 1 for N not equal plus minus 1. Because so we had this factor before of the integral, and we have the only first Fourier mode in the critical interaction function. So apart from N equal plus minus 1, this part vanishes. So it means that we have no root for N equal to 2 or 3 or 5 or something like that. So only chance to get the root of the spectrum function come from N equal plus minus 1. Okay, and then we consider the family of stationary state. So this is a parameter of the family from 0, and the distribution function is something like this. So P horizontal is P, and vertical is x to P, and here that's a broad, and this is more broad. So we consider this kind of family of stationary state. And analyzing this spectrum function, we get the stability of this family, for this family of stationary state. And the result is like this. So we have the critical point 1/2, and here it is stable, and the spectrum is something like, so this spectrum is this. So only continuous spectrum on the pure imaginary axis. And in this side, the left side, we have continuous spectrum again, and then we have root of spectrum function. So as I told you yesterday, the root of lambda function have the quadruple structure. So originally it should be something like this. And now for this Maxwellian distribution, it has a symmetry. So this eigenvalue go down, this eigenvalue go up, the same thing for these. So we have the double degenerated eigenvalues here and here for lambda and minus lambda. So this is the structure of the spectrum. And
for Gaussian.
For Gaussian, so Maxwellian, just Gaussian. My example is Maxwellian.
Okay.
And sorry?
This lambda and minus lambda for this. Are those
Scale?
stable?
Stable. No, so this eigenvalue says there is a stable direction. But this eigenvalue say, oh, I have an unstable direction. So if there is a one unstable eigenvalue, then the state is unstable. The stability condition is all eigenvalue should have the non-positive real part. Okay, so I mean that if we have 100 of stable eigenvalue and only one stable eigenvalue, unstable eigenvalue, then state is unstable. Okay, of course this cannot happen in Hamiltonian system. So this is one example of the stability analysis.
If that solution is exponential to the power minus lambda form, and then that's how you are concluding about stability.
So I just compute there exists the root of lambda 1 and big lambda 1 or big lambda minus 1. And the answer is like that. So in right side, we cannot find any root of lambda 1 and lambda minus 1. Big lambda. And in this side, we can find the root on the real axis. That is the result. Okay. And one comment is this critical point, Tc equal 1/2, is exactly same as start field. So if we perform the computation in statistical mechanics in the HMF model, we get the critical point at Tc equal 1/2. So everything is consistent. So here is unstable, and stability change at the critical point of statistical mechanics. Okay, and then okay, so let me prepare one more important concept of Brasov equation. So this part is a key point for the following topics. So it is the Casimir. So the Brasov equation has a strong symmetry, and it gives the many invariant. What type of invariant? So now we are considering the Q is periodic. And let us consider the C function. It is from real axis to the real axis, and I require the C1 class. So derivative, we have a derivation, and the derivative is continuous. And plus some mathematical condition, I omit. This is not so crucial part, so I omit this. Then we consider this functional So what does it mean? So f gives just a real value. So the real value go to the real value by the function c, and then we integrate over q and p. And the q and p are integrated out, and the remaining variable is t. So this integral may depend on t, but this is conserved. Conserved means if we compute the derivative with respect to t, then it is always 0. So the request of the C function is just a C1 function. We have so many invariants in Brasov equation. The example is like this. If we consider C function like xn, then we get the invariant of this functional. So this functional is invariant. Okay, so we have an infinite number of invariants in Brasov equation. So,
in order to prove dc dt equal to 0,
yeah.
f has to be a function of qp through h, no? Through the Hamiltonian. That is
No,
not required?
no, it's not necessary. So if f depends on q and p only through Hamiltonian, it is stationary.
Okay.
But even in non-stationary state, it holds. So the proof is very easy. So I give you shortly the proof. So maybe this is not the mathematical proof. So we just compute the derivative of this functional, and then we get, so t is here, so we first perform the derivative of c and inside the f, and plus multiplied by df dt and dq dt. And I replace this time derivative with the right-hand side of the Brasov equation. So it is dq and df dp minus dh f dp and df dq and dq dp. So now we observe, for instance, this part and this part is written as dc, sorry, it's parentheses, and dp. Is it okay? So first we perform the derivative of c and then the derivative of f. The same thing for this part. So
Yoshi, when you say C dash, you mean del C del F?
large c,
In the
C prime.
c prime. C prime is so c is now small c is a function, for instance, x. So c prime is c prime means derivative with respect to x. So the next line is dq and dcf dp minus dhf dp and dcf and dq. And then we perform the integration by part. So I move this derivative and this derivative to this part. And I want to eliminate integration by part is something like this. And I want to eliminate this part. So the plus mathematical condition say that this part should be by 0. So if this part is 0, then I can directly go to the next line, the minus dp dq and cf plus dq dp and cf. So this is 0.
So the mathematical condition will mean
This part is 0.
yeah, that the Hamiltonian is bounded or something. I mean the energy is bounded or
So for instance, my previous example is c function is x to power to n, and if f function, so for instance, if we consider the p derivative, p integration, then we need this part go to 0 in the p go to infinite. Okay, and then the f for f is an exponential Gaussian function, so the multiple by of Gaussian function is 0, strongly 0 in the p go to infinity. So this part go to 0, this part go to 0, so it's okay. So this is a simple proof of the existence of Casimir. Yes?
So you said Q
Q has to be periodic when you start it.
Yeah.
Is there, I mean, for this derivation to go through Q, we did not take Q
Ah,
periodic.
okay. So Q periodic is maybe I can eliminate. I can eliminate. So the condition is just, so if Q is periodic, this also. So this part should be 0 because this one, so Q, this part is from Q equals 0 and Q equals 2 pi. So from the periodicity of function, it's 0. So it's easy. But if this part is 0 for the integration of Q, then it's okay. So Q periodic is not necessary. So we should eliminate the periodicity. So this is the key point to understand the all anomaly which I will present today. So from now on, I will present you the anomaly of physical anomaly of Brasov equation. The first thing is no relaxation. In my example, I consider the family of Maxwell distribution, and here is a critical point, and here is the unstable part, and here is the stable part. Unstable, unstable. And then so this one is M. So M is homogeneous part, homogeneous distribution give M equals 0. So this part, this line corresponds to the homogeneous distribution. And then I add the line which represents M equilibrium. So this is the equilibrium value of magnetization or order parameter. So the question is like this. This state is unstable. The unstable means if we give a small perturbation from this line, then state far away from the initial state. This is the minimum instability. And the question is, can this state go to the equilibrium level or not? And the answer is no. So the equilibrium level is here, and I extend the line like this. And I start from the very small value at the initial point. And then temporal evolution of M is like this. So this is the M equilibrium value. And I say this one is the Brasov value. So that's all. So this time evolution do not go to the equilibrium value.
Does this mean there is no unique steady state?
Sorry?
Does this mean there is no unique steady state?
Steady state? Yes. So this one is the steady state. What do you mean steady state? Stationary state?
Stationary state.
Stationary state, okay. So this final state is a stationary state. So more precisely, stable stationary state, but it is not equilibrium. Okay, so yesterday I said if function f depends on QP only through Hamiltonian plus self-constant condition, then this is stationary. So it means the set of stationary state of Brasov. So more precisely, it's a stable stationary state of Brasov include equilibrium state. Equilibrium. But not equal.
So, if I start from a different initial condition,
Hmm?
will it go to some other value, which is not of same thing?
So now my initial condition is says here, and I put a small part modification. So this is one way to give the initial condition. And if we give other initial condition for, so what do you think about the another initial condition? What type of initial condition do you consider?
Maybe like some upper level than where we started with.
Something here. So here.
No.
Here? So here? So maybe no. So even if this, okay. So if we give it a different initial condition, we go to the maybe different Brasov level, but still that Brasov level is not does not coincide with equilibrium level.
Does it mean that the stationary state depends on your initial state?
Yes, yes. So that is a very difficult point of the analysis of Brasov equation. So to get the final state depends on the initial condition, as we said. So to know the final state is a difficult task in Brasov equation. So it is one central issue in this field. Okay.
Yoshi, can one prove that of all possible stationary states, the equilibrium one, the Gibbs-Boltzmann equilibrium is the global attractor or something like that?
No, because so this is counterexample. If it is a global, so this state is global attractor, then this state should go to here.
No, but if n is finite, then it will move away from
n is finite. Okay, so precisely saying this story holds in n infinite limit, and in n finite infinite case, I will talk in short. And I don't know there is the proof if the equilibrium state is a global attractor of the finite n state. Maybe it is very difficult. And it's okay. Yeah.
Will it always be the upper bound equilibrium value is always, I mean, Brasov solution will always be smaller than equilibrium?
The question is, can we expect this value? For this initial condition, I don't expect such kind of behavior. So the reason, so maybe you can understand the reason why we cannot reach the equilibrium value. So I will explain why we cannot reach the equilibrium value.
So Yoshi, this one is that triple S, SS I know is stationary state. What is the other S?
This one is stable.
Okay, thanks.
Stable stationary state. Okay. Yes.
Self-consistent.
This one, a self-consistent. Hmm?
Each part is
Okay. So this one, so if so this one is a self-consistent. So it's the step is like this. We give one the smooth function of phi, and then we consider this equation, self-constant equation. Then the solution to this self-constant equation is always stationary. Okay. The stable or unstable, I don't know. So we have to analyze. But anyway, So if this equation is satisfied, then this F star is stationary. So self-constant equation is self-constant condition is more or less the same thing. And so now I gave the key to understand this no relaxation behavior previously. It's a Casimir. Now maybe you can understand why we cannot reach the equilibrium level. Why? We start from t equals 0 state, and we consider so this is big C, the one of Casimir value, and then we compare this Casimir value with F equilibrium. And in general, this is not equal. Because we have an infinite number of Casimir invariant. So if for infinite number of Casimir invariant, this equality holds, then we are happy. But we cannot expect this kind of speciality in general. So it means because this temporal evolution of ft is equal to f0. Sorry. So this one is not equal to the F equilibrium. So we get this inequality. And it implies Ft is not F equilibrium for any t.
You see, then in this the plot that you have for MV, if your initial one is already Casimir invariant initial state, then you should just remain there. Why you see that?
This one?
Why there is this one?
This bounded?
No, why is it
increase?
Because if I start with an initial state that respects Casimir invariance, so then I should stay at that level, no?
No, because the Casimir invariant, Casimir function is we have integration. So we have integration. So even if we have non-zero m, we have a chance to satisfy this Casimir invariant.
No, so C is not changing, yet M is changing.
C is not changed, but M can change.
How do we see that?
No, I have no intuitive explanation, sorry. Yeah. It's okay. So, and what happened in the...
Okay. So C is a function of F.
Yeah. What happened in finite n? So this is a Brusque level, and here is a equilibrium level, and so if we increase n, we get this kind of behavior. And typical time scale in this trapping time is order n. And first, I comment on this trapping time scale. So I said the tau non-cut is So T, okay. T non-cut is T cut over square root n. So this is the result of yesterday's lecture. And now we have the typical time scale of order n. So T deluxe of non-cuts is, so the cuts, T deluxe of cuts is order n. So it means T deluxe of non-cut is order square root n. So it means that if we consider the non-scaled Hamiltonian system, still we have this kind of long trapping time. So, and if we take go to n infinite limit, still we cannot go to the equilibrium level.
So if you don't do cuts, can you formulate the Blasov equation, because you need that scaling, no? If I remember well.
Yeah. So we need this kind of scale to have the Blasov equation. But if we come back to the n-body simulation and n-body system, then we can consider this time scale. And why it happened? So this one is given by the limit. So we have to take a double limit. So this one, so we start, we take first the T infinite limit, and then L infinite limit. Then we can reach this equilibrium state. But this state is, we first take L to infinite limit, and then we take T to infinite limit. So it means that this double limit cannot commute. And intuitive explanation of this behavior by Casimir is like this. So, yeah?
How did you get the upper cut? Is it through microscopic or?
This one?
Yeah, how did you get the?
So this level? Yeah. This level is equilibrium level. So I have no proof by experience, from my experience.
Not a microscopic numerical simulation which gives us this, or?
So if we perform new n-body simulation, we can reach the equilibrium state. If we perform the numerical computation a very long time. So
you can do microcanonical equilibrium calculation, no? Like all states are equally likely.
Microcanonical, so you mean the microcanonical statistical mechanics?
Yes.
Yeah. So exactly same. Yes, you are right.
Someone can do that calculation.
Yeah. Yeah?
I was wondering, when you wrote down the Blasov equation, you already assumed n tending to infinity.
Sorry?
When you wrote down Blasov equation, you assume system size is infinite.
Yes.
But if you do a finite system size, will there be a correction to Blasov equation? Perturbative correction in 1 over n?
Yes.
And if you do that, do you get this? Or
So I could not understand your question.
if you write Blasov equation,
Yeah?
and then there is a correction to finite n correction.
Yes, yes.
If we solve this equation, do we get a equilibrium?
Okay, yes. Yes. So the Blasov equation is like this. And plus, typically 1 over n, and so-called collision, so C is not Casimir, the collision term. So collision term, it comes from the 2-point correlation. So in n go to infinite limit, we can neglect this part, but if n is finite, we cannot neglect this. And this part drives the system go to the equilibrium state. Okay? And the explanation of this behavior by Casimir is like this. So infinite n, so n goes to infinite, the Casimirs are exactly invariant. But for finite, so n is very large but finite n, Casimirs are no more exact invariant, but still something quasi invariant. So in n infinite, so for instance, this is a counter of Casimir. So this counter is very sharp, but if n finite, the counter may be some ruin of counter, but plus some fluctuation like this. So the system trapped in this region for phi, but this quasi-Casimir is not exactly invariant, so the system can escape from this ruin. And the escaping time velocity is very small, so we get this kind of behavior. So this is the explanation. Sorry? Circle? So circle is the schematic picture of Casimir counter. So for instance, this one. Yeah.
So the way usually people get this curve for when they analyze this quasi-stationary state.
Sorry?
So usually this is the shape of quasi-stationary state that first you get stuck to a metastable state and then eventually move to equilibrium for finite state system. My question is that why only one? I mean, you may have the possibility of getting stuck multiple times.
Multiple times.
So like you start from evolution to state and then you get stuck to one metastable state. You stay there for a long time.
So you expect the symmetry this and this and this?
Stay in a structure.
I cannot reject that proposal, but
there are infinitely many quasi-stationary states close to one. So it does, but then the states are very small because there are infinitely many possibilities.
But I see a sharp transition.
Yeah, because the initial one is not a quasi-stationary state, so this initial relaxation is very fast.
No, not the initial one. I'm saying that once you get stuck to the metastable, then you again sharply move to the equilibrium.
I think it is impossible because this one is unstable stationary state, so the state can move fastly. But now this one is quasi-stationary state, and it is stable. So it corresponds to the stable stationary state of Brussels equation. It is because this is stable, then the movement is, in principle, it is impossible to move from the stable stationary state. But the construction constraint is not exact. So due to from this finite size fluctuation, we can slightly move from the quasi-stationary state. So this is the series of the small movement between the stable stationary state to the another stable stationary state. So from this understanding, in my personal opinion, maybe it's impossible to get a second, so two-step, three-step relaxation. So maybe. So at least I have no experience with that kind of relaxation. Okay. And maybe, okay.
You have defined two times here.
Yes?
Cat time and non-cat.
Yes?
Can you please just explain what does it mean?
This one?
Yeah.
So maybe this one is okay. So this one comes from the Newton equation of motion, and we have the cut prefactor 1 over n, front of the potential.
I'm just trying to physically understand what does these times mean.
This one?
We have written two types, right?
Okay. So if we consider the system with Katz's prescription, the time evolution like this, and then we consider how long time the system can stick in this level. So the typical time scale is order n. So if we increase n, the sticking time gets long. So in Katz's prescription system, the relaxation time, typical relaxation time is order n. And without Katz's factor, the relaxation time is should be divided by square root n. So the time scale is square root n. So still, we have the divergence of the sticking time. Is it clear? Okay. And one part of the participants, the audience, are interested in the Kuramoto model or coupled phase oscillator. So I will comment or one personal opinion that if we can get this kind of behavior in Kuramoto model. So now maybe you can understand yes or no. Okay? So my answer is no. Why? So this behavior is based on the existence of Casimir invariant, and the existence of Casimir invariant is based on the Hamiltonian nature. So as I proved this, so this part and this part is, and finally this part and this part canceled out. So this is important point. So this is based on the Hamiltonian nature. So non-Hamiltonian system, the Kuramoto model, may not have this kind of behavior. Okay? So this is the end of the no relaxation part. Okay.
You see this in Hamiltonian HMF model? You see this kind of
Yeah, so if you perform an n-body simulation, then you can get this behavior.
it's essentially Hamiltonian.
Yeah, so without Hamiltonian nature, personally, I cannot expect this kind of behavior. Okay, we go to the next section. It's a trapping, scaling. And what is the problem? Again, we consider the family of stationary state, and here is a critical point. And we have equilibrium state. And I said this point cannot lead to the equilibrium state, equilibrium the value. So the question is, where is the destination? Oh. And I just give you the idea of analysis to answer this question. So now we have the spectrum, this one and this one. And we concentrate on unstable state direction. Why? Let this give you a simple example. If we consider two-dimensional ODE, and one axis have the instability, and another axis have the stability, and what we want to know is the initial state. So this one is slightly modified from the origin, can escape from origin. And the question is, what is the destination of this travel? And we can understand the destination. Maybe we can understand this destination by focusing on this x direction. Because for getting the destination, at least the distance from the origin, the unstable direction dominates the distance. And this y direction is contracted out. So we can almost neglect this direction. But we cannot completely neglect. Why? Because this travel is not straight. It can modify like this. So we have to, so I say this one, this function is y equal sx, this function. So our strategy like this. First is a projection onto unstable direction. And second, solve Sx. We can do this task perturbatively. And the same thing for the Prof equation. Now we have two unstable directions because we have two doubly degenerated eigenvalues in the unstable side. So we have two unstable directions. And then we project all dynamics onto the two-dimensional plane. And then we do the same thing for the Brasov. And the computation is so complicated, so I skip very long computation, and I give just a result. So
explain the center manifold like that.
So center manifold reduction is center manifold reduction pick up the center direction. So it means the real part is 0. But now we are concentrating on the real part is slightly positive. So a little bit different. In Brasov equation, the center manifold reduction is not a good idea because we have infinite number of it's a continuous spectrum on the real part 0. So it's not a good idea. So this idea is introduced by Crawford. So I give you the reference, PRA, and physics of So if we want to know the details of computation, please read this short paper and long paper. And then we consider this one. So this one is the eigenstate of eigenvalue lambda. And the Hamiltonian nature gives this one is the eigenstate of lambda state, so another lambda plus the remaining part like this. So the remaining part is like this. So this one is, so we consider the psi direction. The psi is more or less eigenvector of eigenvalue, one eigenvalue lambda, and another eigenstate of eigenvalue lambda is just complex conjugate. See?
What are we trying to do actually? What is this y equals to s of x?
Y? This Y? This one is a simple example of the in two-dimensional ODE. So it just gives the intuition to understand what we have to do. So this is not consigned to the Brasov equation. Okay. So the eigenstate of lambda is one eigenstate of lambda is psi lambda, and another one is a complex conjugate, and we project onto the whole system on this two-dimensional space. And then the corresponding part of this Sx is something like this. So we consider the evolution on the curve. So this one, the height is S. And the important point is, so here, maybe I should write down, so A is the function, so F is the function of Q and P and T. A is a function of T, and eigenstate is a function of Q and P, the same thing for this. So what is important is the temporal evolution of amplitude A. And the result is this. The linear part is lambda A because it has an unstable eigenvalue lambda. So linear part is okay. And the next leading term is cubic term. And the cubic term is strangely depend on lambda, and is something like this. So, yeah. Yes. Yes. So, so I give you a small example. Okay, I don't want. I cannot use the. Unfortunately, I cannot use the light blackboard. So I can. No. So let us consider this simple example. So now the lambda and mu is positive, and A and B is some parameter. And we assume y is a function, so this one S, function of S. So this is assumption. And then we derive, so if we input this assumption to the X equation, then we get the closed equation for X. But S is unknown. So we need to know what is S. To know S, we use this one. So y derivative is S prime and X prime. It's okay. And then the right-hand side is Sx plus Bx2. And now this is an unstable state direction, and this is stable direction. So what we can expect is this movement is tangent to the origin. Is it okay? So there's no transversal movement. So we assume this function Sx tangent to the origin. So it means Sx, Taylor expansion of Sx start from S2 and x squared plus something. So inputting this info, so still this one is unknown, and we need to know this one. And then inputting this expansion, we get S2 x, and here is lambda x plus ax sx equal minus mu S2 x squared plus b x squared. So this is a higher order of x, so I neglect this. So I can write down x. So, okay, so I keep this equation. So we can know what is S2. Sorry. So this one is S2. So the first leading term of S function.
Can you please let me logic why it has to be a tangent to the transfer?
So this behavior,
Yeah, why it has to be a tangent?
because we start from this to here, and this direction is contracting direction, so maybe there's no big movement to the y direction. So the dominating direction is x-axis. So first we move to the x-axis, and then the nonlinearity slightly modify the direction. It's okay? So we get S2. Oh. And then, so I input this information to the x equation. Now x equation is ax, and y is sx. Sx is s2 x2 plus something. So ab to lambda plus mu and x plus. So this is the reduced equation. So now we could reduce the two-dimensional equation to the one-dimensional equation, and then we can expect the destination by analyzing the 0 point of this fourth term. So if AB is negative, we can find the solution. What it is? So to maybe, so I need plus minus. So we get this destination, final destination, because we can neglect the higher order. So I assume that we can neglect the higher order. And if AB is positive, with 0, x is 0, and there's no corresponding solution, this one. So it means if we, so for this part, we can compute the destination just only for this one. And for this one, we have no solution around x equals 0. So it means, so this is the x. So for this one, maybe we have this kind of behavior, for instance, the lambda dependence of x. But for this, we have no solution around x equals 0. So it means if there is something happen, we may have discontinuous bifurcation. So it is suggested from this analysis. And the same, we can do the same thing for the Brasov equation. And the final equation is, instead of this equation, we have that dA dt equal lambda or something. And now C cube, C3 is minus lambda cube. So it means ordering of A should be order lambda square. And now I input the lambda should be linear order of the distance from a critical point. So it means it is square. So the answer to the first question of this section is like this. T, M, and this is equilibrium state, and here is Tc, 1/2. And if we start from here and here and here and here and here, and then the destination is like this. And this part is M is order Tc minus T and half. But this part gives M is order T minus T, sorry, Tc minus T squared. So this is the result. So it means the final destination is strongly suppressed comparing with the equilibrium level.
Can you go to that argument once more?
Outside?
The one that, okay, so A naught is order lambda square.
Okay.
And so that is like
Okay. So if the right-hand side of the top equation is 0, then it may correspond to the final destination of A, amplitude A.
How do you get these two scalings, like 1/2 and 2?
1/2 and 2. Wait, this one? This one. Oh, up and down. So we have the dA dt equal. Okay, and A is so if we solve the equation, we have a lambda square, and we may expect the lambda is it's okay. So it is a square, and square root part is the simple. This is a result of statistical mechanics.
Sorry?
This is a result of the statistical mechanics for mean field system. The square root dependence is in equilibrium. The mean field system have so this is a critical point beta, and beta is 1/2 is so.
Okay. So therefore, close to the critical point, I may see a different scaling exponent.
Yes.
Depending on whether I am in equilibrium or in a quasi-stationary.
Yes, exactly.
Why that C3 lambda scales with -1?
So that's the result.
That's a result of long computation. But still, even in this simple example, you can understand the appearance of singularity. Why? Now I assume the mu is a contracting direction, but in Brasov equation, there are many real zero spectrum. So maybe I can eliminate this. So this may be 0. So you have 1 over lambda factor here. So in the limit of lambda go to 0, it has a singularity, even in this simple example.
Why are you
Hmm? Negative? The mu? Okay. So mu is the strength of the contraction. Okay? And in Hamiltonian system, the many spectrum is on imaginary axis. So real part is 0. So instead of exact 0, I input real part is 0 into this equation. So it's not a rigorous computation, just an intuitive understanding why we have the singularity in lambda.
So these two scaling exponents, 1/2 and 2, have they been observed for the HMF model?
1/2.
This magnetization.
This one?
Yeah, there are two scaling, 1/2 and 2.
1/2 and 2.
Have they been observed in numerical simulation?
Maybe yes. So for this, I am sure. This one, I'm sure.
This one is more, the equilibrium one is more straightforward, but this one has been observed, 2.
So I think if we use a finite n and we compute a long time, then we can reach the equilibrium state. This is my experience. So we can get this exponent for finite n and a long time. And for this, if we use the Brasov code, and then we get this exponent. Brasov code or finite n, and that's a short time, because the behavior is something like this. So we should stop here. Okay. Analytically? I haven't derived analytically. So we can compute the C3 factor in the Brasov equation after long computation. And then we get the C3, so 1 over lambda cube factor. So it's fine. Oh, 15 minutes left. Okay. So quickly, I present so maybe this is the last section. So 9, the response. So the problem is this. So HMF model consists of n particles on unit circle. And then we apply the external force or magnetic field, if you like. Then the magnetization, initial magnetization, go to new magnetization with external force H. And we consider the response to this external force. So we have two critical exponents. In off critical, MH, depending on T, is chi T times H plus higher order term. And chi T is proportional to T minus Tc power to gamma. So this one is critical point. Sorry, critical exponent. Another critical exponent is on critical and MH at Tc. Now, on critical, linear response coefficient diverge, so we cannot define the linear response. So response should be nonlinear. So nonlinearity is characterized by this critical exponent. So another critical exponent. So what we want to know is this critical exponent. And statistical mechanics say so now we have the m is proportional to Tc minus T square. So this is another critical exponent beta. And here we can get the gamma critical exponent here and here. And the gamma, I said plus is 1. And the gamma minus is also 1. And at the critical point, we get delta equals 3. And these three critical exponents satisfy the scaling relation. This. Okay. So this is the result of statistical mechanics. And our interest is how about in the Brasov dynamics? The final destination of the response is also trapped before going to the equilibrium level. So we can define the same critical exponent for the Brasov non-equilibrium state. And how to analyze it? So question is, now we prepared the branch. So the beta is 1 over 2. And we know the gamma plus minus and delta in Brasov. So maybe I have no time. So I wanted to show you the method to analyze, but I should skip. And I give just answer. The Brasov equation gives. So this is the reference state. It corresponds to the M0. So the beta, as I said, so beta should be 1/2. And the gamma plus is, fortunately, 1. So this is the result of one theory. And strength in this gamma minus is beta divided by 2. So in this case, 1/4. And at the critical point, delta is 3 over 2. How about the scaling relation? We have this, sorry, this is plus minus. So this one, but not this one. So this is the result of analysis in Brasov system.
So one is kinetic calculation, and the other is you are considering in field dynamics with Brasov.
Yeah. So this one is very simple. We compute a partition function and compute a critical exponent. It's okay. And this is we consider Brasco dynamics, and the dynamics response temporal evolution of M is something like this. So we start from M0. So M0 is here, for instance. And then we applied external force. Then magnetization increase. But it is smaller than M equilibrium with H. Okay, so we consider the critical exponent by using this magnetization. And then we get this strange critical exponent. So in the last 5 minutes, can you use the screen? I give you the result of the numerical computation for confirming this result. Oh, I should like the in this side. So for this moment, do you have any question? It's okay. Okay. So, statistical, as I said, the statistical mechanics gives okay. It come back. So the beta half and gamma plus minus 1 and delta 3 and dynamics, Brasco dynamics gives 1/2 and 1 and 1/4 and 3/2. And this is a result of a numerical experiment. So n-body simulation for confirming the gamma minus is 1/4. So forget about the blue line. So please concentrate on this red line and the purple point. Red line is a result of theory. I could not show. And the purple point is a result of the n-body simulation. And then they coincide very well. And the important point is this slope has a slope minus 1/4. So now beta is B is 1/T, so beta. So, and this is a distance from the critical point. And this slope has a minus 1/4 means critical exponent gamma minus is 1/4. So 1/4 is confirmed, has been confirmed numerically. Okay? And the next one, at the critical point. On critical, theory said we have exponent 3/2. And how about this? So this one is horizontal axis is intensity of external force, and a vertical axis is magnetization. And the important information is very difficult to control. So this red part is exactly at the critical point, 0.5. And then the dependence on H of the response has a slope 2/3. Okay, so 2/3 means M, H, so Brasov H is H 2 over 3. So it means h1 over 3 over 2. So this is delta. So delta is 3 over 2. It's okay. And if we, so other point is the high energy part. And if we take a high energy part, we get the normal slope 1. So linear response is coming back. Okay? So why? Okay. Oh, I want to back. The last comment is we have the different critical exponent in the high energy side and low energy side, gamma plus and gamma minus. Why? The intuitive explanation is like this. So we have, again, Casimir invariant. And in the high energy side, Casimirs are not obstacle of dynamics, so response. Why? So dynamics, so if we at the external force, the initial state go certainly move to the another place, but it is tangent to the counter of Casimir. So Casimirs are not obstacle. Then we get the same critical exponent with statistical mechanics. But in low energy side, the dynamics is not the, so dynamics should along to the counter of Casimir because of the Casimir invariant, but the statistical mechanics does not concern to the Casimir invariant, so the direction of the movement is not tangent to the Casimir invariant. So now, in this side, Casimir's invariant are real obstacle of response. So response is suppressed. Is it clear? Okay.
Why is it why is the difference coming? Sorry, I didn't get it. In one case it is tangent, in the other case it is vibration.
So this is a.
You have to prove it.
Okay.
What?
So in one.
No, I am not asking you to prove it now, but you have proved it.
Okay. So this is my intuitive understanding. So I have no mathematical proof, but rough estimation of the direction of Casimir gives this kind of picture. So the short explanation is like this. So in this side, so state have no Q dependence in first, and then it have the Q dependence, but very small Q dependence. And the small Q dependence does not change the Casimir by analysis. So I have this kind of picture. So if you are interested, I explain later in detail. So final message is this. Oh, sorry. So I prepared the finite. So I just comment on the finite size fluctuation. So we have the fluctuation response relations, and now we have the anomaly in response. So we can expect anomaly in fluctuation, and it is true. So it's all with the final section. And the final message is this table. Today I showed several anomalies in the Brasser equation. Relaxation does not occur in Brasser equation, and we have a strange critical exponent in the Brasser equation, and another anomaly is the finite size fluctuation. I could not show you. But so anyway, we have many anomalies in Brasser equation comparing with statistical mechanics. And all of these anomalies come from the existence of Casimir. So this is a key point to understand the anomaly in Brasser equation. Okay, thank you very much.